The QED-C is a consortium of 160 stakeholders that are in the quantum information industry here in the United States. It was chartered under the National Quantum Act. And what we're doing with the QED-C is working to create a robust commercial quantum industry and the associated supply chain here in the US. It includes manufacturers, users of components, developers of quantum systems and products that enable quantum technology. And the real purpose of the QED-C is to foster a strong quantum information ecosystem, primarily through the development of those enabling technologies and funding their development so that we have a robust supply chain. In addition, we're also looking at standards and workforce development, as well as those use cases that are driving the quantum industry forward. There really are 5 or 6 general groups within the 160 stakeholders, corporations, universities, national labs that comprise the QED-C. I can enumerate the 5. The first are probably the quantum hardware developers. These are companies like IBM and Microsoft and Google and Rigetti and IonQ and others, PsiQuantum, that are developing actual quantum hardware. Now, those are for the computational industries, but there are others like Cold Quanta and AOSense, Honeywell, that are developing quantum sensors for the sensing industry. And then you have others like AT&T and in association and in collaboration with universities that are developing quantum communications hardware. So that's kind of the first and large group. The second are those suppliers to those hardware developers. These are the people that are building the components that I spoke about that are employed in and provide components to those quantum hardware developers. The third group that comprises the QED-C are software developers. They're the people that are developing the software so all of this can run smoothly. A fourth group is the research community. Those are sometimes indistinguishable from the industrial community, but there are very, very close collaborations. And we're seeing a culture shift where the research is really being done in a very collaborative way between industry, national lab, independent research laboratory, and the universities. That is kind of the fourth large community. And then the fifth are the end users. These are members of the QED-C like Citibank, Wells Fargo, the Federal Reserve Bank of the United States, where they know that their business is going to be impacted by quantum information science. And so they want to be ahead of it. They want to be up to speed on what are the standards, what is happening in the industry. And that provides or comprises, if you will, a fifth large group within our consortium of 160 members. Quantum information science really is a fusion of two of the most powerful forces in scientific discovery in the 20th century. It's quantum science fused together with computer science. And it's that convergence of information science and quantum physics that makes quantum information science so powerful. Simply put, it offers new ways of gathering, processing, and disseminating information that can provide considerable advantage over classical computation and classical ways of doing these things. Quantum 1.0 is really the notion that you take advantage of the quantum properties of materials the way they're actually found in nature. For example, the band gap in a semiconductor led to the practical implementation of a transistor. But those band gaps are things that are found in nature. And while we can alter them slightly, in Quantum 2.0, we purposely engineer quantum properties into materials to take advantage of their quantum behavior. And particularly, we're taking advantage of the quantum behavior of superposition and entanglement in order to create qubits. Qubits are a quantum bit. And this is the difference between 1.0 and 2.0. In the first 100 years of quantum science, we were very, very focused on exploiting the technologies, or developing technologies that exploited the properties of physics in nature as we found them. Whereas in Quantum 2.0, we're really engineering quantum properties into materials and into devices that we can now take advantage of and exponentiate that capability with both entanglement and superposition properties. Quantum computers are vastly, exponentially more powerful than a regular computer. More computing power allows computers to really solve harder problems. And in fact, problems that cannot be solved by digital computers at all. And I don't want to just focus on the computational aspects of quantum. In addition, we have quantum sensors and quantum communications. Those are really actually some of the first movers where you're seeing a real inroads in the quantum industry. Quantum sensors detect things that classical sensors cannot. Very minute signals, very minute fields. And those are useful for advanced navigation or medical diagnostics. Quantum communications offers provably secure communication channels and the ability to network quantum computers and sensors together. And so all of that combined is really leading to unprecedented levels of performance that are way beyond what the classical counterpart can perform. One of the large barriers that's standing in the way of quantum commercialization today is the fact that in a typical quantum research or commercialization project, let's say that's 5 years in duration, 5 years long, the first 3 years are often spent sourcing equipment, sourcing components, customizing those in order to be employable within that quantum system that you're prototyping or developing or doing research on. The number of enabling technologies available is limited, and typically they're not servicing the quantum industry itself, but in fact, they are components designed for some other industry that then have to be adopted. In order to speed the innovation cycle and the commercialization cycle, what we hope to achieve is a robust supply chain of those enabling technologies so that instead of spending 3 years to get an experiment up and running or to develop a quantum prototype, that we could shrink that time down to, say, 3 months. And that would be because the developer, researcher, industrialist could find ready-made out there in the marketplace exact devices fit for use that they need for a quantum program. I think the first applications are actually already here. You have commercial applications of quantum technology today in the form of GPS, and that's been launched since 1983. Atomic clocks have been rapidly followed by quantum sensors. Quantum sensors are increasingly ubiquitous. We're seeing them implemented in medical devices. We're seeing them in the oil patch. We're seeing them for mineral deposits, and we're seeing them in the applications of precision navigation. And then finally, you have quantum computers. That'll probably be 3 to 5 years from now when they will be more ubiquitously employed. But you'll see them attacking problems being solved on them that currently are just simply unsolvable today, as Google demonstrated last October with their demonstration of quantum supremacy. Certainly, the United States is leading, and China is also a leading player. That's closely followed by Europe, and there are some tremendous advances and innovations occurring both in the EU, and then the United Kingdom has a very, very strong quantum industry that's emerging. Each one is kind of picking their own specialties. There's tremendous collaboration occurring among them. In addition, I have to mention Canada, our neighbor to the north, with Waterloo, with the Quantum Valley Innovation Hub. This has been a tremendous source of innovation for globally. And I also would be remiss if I didn't mention Australia, and their contributions have been tremendous. They have just in the last month or so outlined their own quantum information initiative within Australia, and they are growing their quantum industry as well. I think that the outlook for the QED-C is extremely bright. And, it couldn't have been done without the vision of a large number of people, both within government and within industry, that got together to write the National Quantum Initiative and then took it further in order to support the National Quantum Initiative Act of 2018. It was out of that act that the QED-C was born. And I guess the one thing that I would like to say here in conclusion is that we owe those visionaries, those people within many of the private companies that are in the QED-C today, as well as from professional societies, as well as the people at NIST, particularly Carl Williams and Jake Taylor, who really had the vision for the Quantum Economic Development Consortium and saw to it that it would be carried out and through legislation and then put into effect. So I think all of us that are benefiting from that vision should be very grateful to those people that in the last 5 years, so much effort has been focused on making sure that we have a robust quantum industry, that the United States maintains its leadership and its economic and national security through quantum information science.